Welcome to this explainer. Look, if you're a computer science student staring down an upcoming exam, I know exactly how you're feeling right now. The pressure's on, the syllabus looks literally endless, and data representation, well, it can kind of feel like an entirely different language. But hey, take a deep breath. Today, I'm going to be your personal tutor. We are putting you through a rapid-fire data representation bootcamp. Our goal? To secure those easy, guaranteed marks on past paper questions that examiners absolutely love to ask year after year. We're going to strip away the noise and focus purely on what you need to know to perform. Okay, let's dive into this study plan. 1. Number systems demystified. 2. Mastering 2's complement. 3. Binary addition and overflow. 4. Navigating logical bit shifts. And 5. Memory addresses and applications. This roadmap covers exactly what you need to master for the exam. Section 1, Number Systems Demystified. Grasping the differences between these foundational building blocks is absolutely crucial. Grasp this, and the rest is just following patterns. So there are 3 main languages of computer science you need to know. First up, binary. It's base 2, using only the digits 0 and 1. Why? Well, because at their core, computers are basically just billions of tiny switches that can only be on or off. Then we have denary, which is base 10, using digits 0 through 9. That's our human world, it's how we naturally count. But then we have hexadecimal, base 16. It uses 0 through 9, and then the letters A through F for 10 to 15. Now, computers don't natively think in hex. Programmers use hexadecimal because it acts as a much shorter, way less error-prone representation of long binary strings. It's a shorthand, right? It saves time and drastically reduces mistakes. All right, let's put that to the test with a classic past paper question. If you see this on the exam, convert the denary number 234 to binary and 26 to hexadecimal. Mentally practice this with me right now. For 234 to binary, you're fitting those base 2 place values, 128, 64, 32, into 234 until you hit 0. Easy enough. Now for 26 to hexadecimal, you're asking yourself, how many 16s go into 26? Well, that's 1 16 with 10 left over. And remember, 10 in hex is A, so the answer is 1A. Boom, full marks. Section 2, Mastering 2's complement. Now, this is a notorious area for simple calculation errors under exam pressure, representing negative numbers. The cool concept you absolutely must memorize is 2's complement. If an examiner asks you to define how negative denary numbers are represented as binary, this is the exact terminology they are looking for. It's the mathematical operation computers use to represent both positive and negative integers within the same binary system. So let's look at how this actually appears on a real test. Here's a direct exam question sourced from a past paper. A character in a game has a health value of -25. Calculate the 2's complement 8-bit integer. Examiners love wrapping these questions in real-world scenarios, like gaming. But hey, don't let the scenario distract you, because the math remains exactly the same. Okay, here is your whiteboard breakdown. Step 1, completely ignore that negative sign for a second and just find the standard 8-bit binary for +25. That gives us 000-11001. Step 2, flip the switches. Literally invert every single bit. The zeros become ones, the ones become zeros. So now we have 111-00110. Step 3, and listen, this is my major pro tip for you, never ever skip this final phase when the clock is ticking. You absolutely must add 1 to that inverted result. That gives us our final answer, 111-001-111. Honestly, write those 3 steps on your scratch paper the absolute second you sit down. Section 3, Binary Addition and Overflow. Now, what's really interesting here is what happens when computer math hits its physical limits. You are frequently going to be asked to add 2 8-bit binary numbers together. Let's imagine a scenario from a specimen paper where the calculation mathematically results in a denary value of 301. The question asks, this generates an error. Why? Well, think about an 8-bit register for a second. The absolute maximum denary value it can hold when all 8 bits are turned to 1 is 255. So 301 physically cannot fit inside an 8-bit space. No way. Before we answer the why definitively, I really need to interject with a crucial piece of exam strategy. When you're doing binary addition on paper, please perfectly align your columns. I literally cannot tell you how many marks are lost just because a student rushed, their handwriting got sloppy, and a 1 drifted into the wrong column. And for sure, always explicitly write down your carryover bits so the examiner can actually see you're working. So, back to our error of 301. What is the precise textbook definition you need to write down to secure full marks? It's an overflow error. You write, an overflow error occurs when the answer is too large to represent in the number of bits available. Memorize that sentence verbatim. It is the gold standard answer the marking scheme demands. Section 4, Navigating Logical Bit Shifts. Let's move to this and see how it builds, because examiners absolutely love to test this. It bridges the gap between physically moving data and mathematical operations. First off, you need to lock this contrast into your memory. A logical left shift physically moves the bits to the left, which mathematically multiplies the original binary number. A logical right shift moves the bits to the right, which mathematically divides the binary number. Simple rule. Left is multiply, right is divide. Okay, let's tackle another specimen paper question together. You have the binary value 01010010 in an 8-bit register. You're asked to perform a logical left shift of 2 places. Mentally visualize this with me. You grab all those ones and zeros and just slide them 2 spots to the left. The 2 bits on the far left, they fall off the edge into oblivion. And because you shifted left, you now have 2 empty spots on the far right. You just fill those empty spots with zeros. And here is a beautiful mathematical shortcut that examiners frequently ask about as a follow-up. If one shift to the left multiplies the value by 2, then a logical left shift of 2 places multiplies the original value by 4. If you shifted it 3 places, it multiplied by 8. Recognizing this pattern saves you from having to convert the whole thing back to denary just to figure out what happened. Game changer, right? Section 5, Memory Addresses and Applications. So the crucial point here is understanding how all these raw ones and zeros actually translate into functioning computer architecture. You will almost certainly see a question about MAC addresses. Media Access Control addresses are prime real estate on the exam. They're typically represented in hexadecimal, like the example from the papers, 97-5C-E1. A MAC address uniquely identifies a specific device on a network. It is the perfect example of why programmers use hexadecimal. I mean, imagine trying to read or type out that MAC address in pure binary without making a single typo. Nightmare. In fact, if the exam asks you to list other uses of hexadecimal in computer science, you need a ready-to-go list. Here is your rapid-fire ammunition, straight from the marking schemes. MAC addresses, memory addresses, which, by the way, debuggers look at when a game character isn't moving right, HTML color codes for web design, and system error codes. Memorize 2 or 3 of these, and you've got guaranteed points right in your pocket. Finally, let's briefly touch on data storage and compression. Past papers absolutely love this scenario. An employee emails a text report. Why must they use lossless compression instead of lossy compression? Think about the logic here. If you use lossy compression on a photograph, dropping a few pixels might make the sky look slightly less blue, but, you can still tell it's a sky. If you use lossy compression on a text file, it permanently deletes letters and words. The report literally becomes unreadable gibberish. Lossless compression ensures the exact original file is perfectly reconstructed. And just like that, you've survived the boot camp. You've totally got this. Remember the core rules. Practice your conversions until they're just muscle memory, mind the direction of your logical shifts, and for the love of all things, double-check those carry bits during binary addition. As you walk into that exam hall, leave feeling confident. But it begs a bigger question, doesn't it? If mastering just 2 numbers, 0 and 1, literally unlocks the foundation of our entire digital universe, what else are you capable of decoding? Good luck on the test, and thanks for joining me for this explainer.